So we are all set, I think. Okay, good. So are you able to see my screen? You are, right? Okay, I can see that. Okay, fine. Okay, so the last thing that we saw in the last class was trace inclusion, right? What does it mean to do trace inclusion? This is precisely corresponding to the definitions that we had seen here. Let me take the screen. Yeah, so these, we had trace inclusion on left side. So you can say command 1 is included in command 2 if all the traces that are generated by command 1 are subsets of traces generated by command 2. And trace equivalence is they generate the same set of traces, right? And this is what you want for simple compiler correctness. The simple correctness, compiler correctness property is that they produce the same set of traces, but also they match one to one, right? This is what we had seen in the simulation relation, where he said for every state in the original program, right? You sort of think about this R as relating the original program and the compiled program, the optimized program. So for every state, every transition that you take in the original program, if you can take a step with the label L, then you can take the same step in the optimized program as well, right? And we said this R is a simulation relation if it respects this particular property, right, which is described here pictorially. And then we also have this property that they agree on termination, which is that if the left-hand side is at skip, the right-hand side is also at skip. So this is sort of how to relate the final state. So what we are going to do is to sort of look at encoding of all of this in Core. And we had gotten all the way to trace equivalence. So let's actually look at a program that we want to optimize, right? So here is a very simple program. The point of this program is not to do anything fancy, right? It's like a very simple example. It's not even correct, right? So this is going to print the number of days in a month. It is going to compute it in a very strange way, and it's going to keep outputting the number of days in a month in an infinite loop, right? So um, I'm going to be very imprecise what a month means. So I'm going to say a week has 7 days and a month has 4 weeks, right? 7 fours are 28. So every month in my simplified year is going to have 28 days. So I'm going to print the month boundaries here. This is the program that we are going to optimize. So initially accumulator is 0 and I have while 1, right? So this loop never terminates, right? So this is just going to go forever. And recall that when this when command is really if. So I'm checking if days per month. Again, this is always going to be a positive value, right? Because we know days per month is going to be 7 times 4, right? So when days per month, then accumulator is accumulator plus days per month, and then output the accumulator. So it's going to print 28, and it's going to go all the way, print 56, keep printing, adding 28 and printing it, right? And there is this else branch, which I know for sure I'm not going to take, right? So the point of this very simple program is to just illustrate the optimization, right? So this constant folding optimization. The days per month here is not a constant, right? It's an expression that is actually 7 times 4. When I write 7 times, when I write this term here, and then I do percentage arith, I'm sort of saying consider this as an arithmetic expression. So if you look at check days per month, right? That's an arithmetic expression. That's not a natural number. I think if I don't include it, we will consider that as a natural number. So this has done the computation, right? So this is sort of saying 7 times 4 is 28. But I'm not doing that. I'm just using the star as a notation from earlier. I'm actually defining the arithmetic expression. You can actually print it. You can see what it is, right? When I print it, I see that the arithmetic expression is composed of two sub-expressions. Actually, it doesn't print the constant numbers, but days per week and weeks per month are actually constants, right? They are 7 and 4. This is just Coq not printing it. The way you should think about days per month here is that you actually have when 7 times 4, then accumulator is accumulator plus 7 times 4. And our constant folding optimization is very simple, right? So it's going to find the maximal sub-expression, which is only composed of numerical values, and it's going to sort of reduce that to a constant value, right? So that's what this is going to do. We want to optimize this to 28, right? And it's so simple that we can see that this optimization does not change the outputs at all, right? But we have to sort of convince Coq that this is in fact the case. We do that through simulation, right? So here is the program, right? And we can we add some externs, right? We add some externs for help. So we are saying that whenever we find interp of underscore underscore equals underscore, we simplify equality, and underscore underscore not equals to underscore, we also simplify equality. We had seen external rules in logic programming, right? It just says that when I issue auto or e-auto, if you find this pattern, right, you just go ahead and try simplify equality. If it doesn't work, come back and do something else, right? This program is very simple, but this program is also complicated in its own right. The fact that this program infinitely prints outputs is going to make it complicated. So if we perform an optimization, we cannot just execute the program, right? Get the list of outputs and then say that, look, the outputs are the same. We have to sort of reason about the program in terms of its traces, right, that it can generate. And the traces, by definition, could be any subset of the outputs as well, right? By definition, we cannot run this program and get the full trace and show that these lists are the same. That's the challenge here, right? And that is why this program is interesting. We can, in fact, do something simple, right? I can show that if you run this program, right, because traces are sort of include all prefixes as well, right? If a program produces a trace, any prefix of the trace is also a trace that is generated by the program. I can, if I execute this program under an anti-evaluation context, right? One of the traces that is generated is going to be 28 and 56, right? So the first two outputs that you see for this is 28 and 56. I can show it moderately with some tedium, right? So with moderate complexity, I can actually show that this is in fact true. This is very mechanical, but I just want to get the point across. So that's the program, and we know that this is a function. This is a definition, right? So an example is also a definition. So unfold that. So the first step, right? So what does generate do? Generate has several rules. One of that is truncation. Another is actually outputting. Another one is silent rule. Another one for termination, right? So if you look at the execution here, I'm going to evaluate this assignment first. And this assignment is not going to produce an output. And the corresponding rule in generate is gen silent, right? Just to recall, let's print generate. I have an extra. So if you look at what we have, so we have done for truncation, right? We have skip, that is the actual termination. Silent is for any other step that doesn't produce a value, so that's none, right? So this is going to produce a silent label, and then there is an actual output where you get an output here, right? And the only thing that can produce an output is the output command. So the first thing is we are reducing here in this program, we are going to first reduce this assignment. Because that is going to fall under silent, I'm going to say I can take a step by applying gen silent. When you do gen silent, it says, okay, you're going to have the same list as output, right? And you're going to take a C step, and that's not going to produce any output, right? That the label is a silent label. Now you just show that you can reduce this once, right? This is a unification variable. So we just have to apply rules for reducing it. As we've seen earlier, this is a C1 semicolon C2. The rest of it is just a while loop, right? And here I'm going to reduce this sub expression first. So the evaluation context that I'm going to choose is C seek whole underscore, with the idea that I'm going to execute whatever falls in this hole, which is this assignment, right? And I'm going to do E auto. So if you do this, that particular thing gets evaluated fully, right? And again, now I have skip semicolon this whole thing. In order to reduce a command which has skip, the whole thing should be taken as a whole. And we have a rule which reduces the whole thing to just the skip semicolon C to just C, right? And hence I choose the next step to be a whole. And this also does not produce any output, so I'm going to do gen silent again, right? So if I do this, then whole thing reduces. This can keep going, right? You can keep doing this until we get to this point. Yeah, so here. So you keep doing this until you get to this expression, which is the first expression is output accumulator, then do this loop again, right? And because output accumulator is going to produce a result, right? That is, it is going to produce sum 28. I'm going to do gen output. So what this says is that the head value in this output should have come from this particular reduction, right? So this says this should produce sum 28, and the tail is just going to be the tail of the list, right? And the rest of it is just the same, right? So I'm going to reduce this term. So I choose the C seek whole underscore because this is a sequence command, with the first command being output, second being while, and then you do E auto. This will go through, right? So we have output at 28, that's gone. So now I have 56. You keep reducing step by step, right? Until you again come to this step where you're going to output the accumulator. The accumulator is now 56, right? And now you say E apply gen output, right? And then we have the output here. You just say reduce it one step. That's gone. So we've also output that step. If you look at this program, right, this program just keeps going. You can keep evaluating it, but we know that you can truncate the trace at any point, right? So we just call constructor here, which is basically apply. What is it called again? I forgot the name. Gen done, right? So that is the rule that is being applied. Gen done. So when you apply gen done, because let's do check gen done. So if you look at gen done, for any valuation command, right, para valuation command, gen done matches with the empty trace, right? We have an empty trace here. We have some valuation command. I don't care about what it is. I'm just saying I'm going to truncate the trace here, right? So what I've in fact shown is that if you execute this program, the first two outputs are sum 28 and sum 56. The first two outputs in the trace. One of the formal way of saying this is one of the traces that it produces is sum 28 and 56. This is fine, but we want to say something about applying optimization on this program. And because this is an infinite program, we have to do this in a clever way, right? We can't just say execute the program and you will get this result. So in order to do that, let's first define the let's first define the optimization, right? The optimization is we are just constant folding arithmetic values, right? So um, this does the main work here. So if you have an arithmetic expression which is plus e1 e2, you constant fold e1, constant fold e2, you get e1 prime e2 prime. If both e1 prime and e2 prime are constants, right, you just replace that with the constant expression, which is the whose value is n1 plus n2. So this n1 plus n2 is actually, you can sort of think about them as compiler statically computing the value, right, and replacing that with this constant expression, right? And similarly for minus, similarly for times, right? So that's the definition for constant folding on arithmetic expressions. This constant folds maximal sub-expressions, right? As long as the expression is full of constants to whatever depth, it's going to replace that with a single constant. So we can show that this is in fact the case, right? So if you say I have for any valuation, any expression, right? You can optimize this expression, right? Constant fold the arithmetic in this expression, and if you interpret the expression in V, that's the same as interpreting the original expression in V. This is very trivial, right? Because we are only taking, we are only folding the constants, right? Constant expressions. And you can prove this by induction. So we prove this by induction on E, simplify and try equality for making the basic cases go through. And all we have is, we have a one match here, another match here. And because we have matches, we are going to do case analysis, right? So we are going to do case analysis on the first match, simplify and try equality. One of that is gone, and we have the second match with here. I'm going to do case analysis on that, and this actually proves that this is in fact the case. This proof is very simple, right? That's just a helper thing that we have on the side. So we know what is the meaning of constant folding on arithmetic expressions, right? Now we have to lift the constant folding to our command language. Our language, recall that our language has an expression language, right, and a command language with sequencing, while, and if, and so on, right? So how do you constant fold on expressions? Very simple, right? So wherever you find this arithmetic expressions, right, you constant fold on the arithmetic expressions. So if you have a sequence C1, C2, you recursively constant fold on the expression C1 and C2. And eventually, whenever you find this arithmetic expression, you are going to call C fold arith, which is this definition, right? And that appears on the right hand side of the assignment, the predicate for if and while, right? So these are going to be constant folded as well. C fold arith and output, right? So wherever this expression appears, we are going to do constant folding. So how does it, what is the effect of applying this optimization on our very simple program? So we have the original program here, right, which is days per month. Again, this days per month is, you read this as 7 times 28, right? And we have, sorry, 7 times 4. We have 7 times 4 here, 7 times 4 here. When you apply the constant fold expressions on this program and compute the result, what you end up getting is the constant 28, right? And what we need to prove is that this program produces is equivalent, right? The meaning of this program is equivalent to this meaning of the optimized program. The traces that are produced by these two programs are in fact the same, right? Any questions on this so far before we dive into the proof of simulation and so on? No questions. Okay. So far so simple, right? So what we will do as we are going to look at this one is that there's something interesting here, right? So this simulation relation here says that there is some simulation there is some relation R that relates B comma C to V comma C, and it has two properties that they agree on termination, and that if the left hand side can take a step, then the right hand side can also take a step, right? And what we will in fact prove is that if you happen to have a relation that satisfies these two properties, right, then I can in fact show, without knowing what this relation is, this relation could be arbitrarily specific to the optimization that you're doing. As long as this relation satisfies these two properties, I will show that the traces that are produced for S1 and S2 are going to be equivalent, right? So I'm going to show that these two states are going to be equivalent states in terms of the traces that they can produce. So we are not going to focus just on constant folding here. We are going to develop general techniques, just like how we developed general techniques for proving with invariance, right? We had invariant induction, invariant weakening, and so on. This is just a very general technique for reasoning about program equivalence, right? So what does it mean to say two programs are equivalent? Assuming that they match, the steps of the program match one to one, right? If the left hand side program can take a step, the right hand side program also take the same step. If you can show that these two properties hold, I'm going to prove that they are in fact equivalent. I have to show that the traces that are produced by the left hand side are the same as traces that are produced on the right hand side, and the same and the other way as well, right? So okay, so this is what I'm going to do, and for this um, I think I have one more slide. No. Okay, I think I have it here. So for this, what I'm going to do is, yeah, this one. Just a second, I'll just export this to PDF. Fine. So if I don't do PDF, yeah, it's sort of I can't see the rest of the screen. So what is this one? Give me just 1 second. Okay, here we are. Okay, so this is what I wanted to have. So let's make it full screen. Okay, so what I am going to do is to actually do this proof, right? I'm going to prove that assuming these two properties, this equivalence holds. And in order to do that, we have to do the two inclusions separately, right? So, so this trace equivalence is in fact defined by both the inclusions this way, right? So that the left-hand side traces are included in the right-hand side, and the right-hand side traces are included in the left-hand side. That is what I have down here. I'm going to do the proofs of them separately. In particular, I'm going to prove that for every step that you can, for every trace that you can produce here, I produce the same trace on this side. And assuming the same set of simulation relation properties, I'm going to show that assuming that I can produce some step here, right? I can produce the same step on this side as well. So this is what I'm going to do. And yeah, the left to right is done by induction on the traces, right? As we will see, this is going to be straightforward. So I'm going to show some property that this is going to be, I'll do induction. I'll show that for every step I can have an equivalent step here. But the right to left proof is going to be a little bit tricky in the sense that I'm going to depend on two properties. I'm going to depend on the fact that our operational semantics is in fact total, by which I mean um, every configuration, right? Every state where the command is not a skip, can take a step, right? It does not get stuck, right? So unlike this is very closely related to the point, the concept of type safety, right? Um, it is true that untyped lambda calculus terms can get stuck, but even without types, right? Our language that we have here, the command language here, is so simple that it will never get stuck. If you can write down a particular program in our language, then every at every step you can always take a step, right, until you get to a value. So it's a if you think about it, it's an interesting property, right? Even without types, we are actually proving that we will never get stuck. We depend on that here. We will actually prove that our semantics is total and that our semantics is deterministic. So we will use this property that if you have a state S1 and you take a step to say S1 prime, and you have a state, and for all states that you can take a step from S1, which is S1 double prime, S1 prime and S1 double prime are the same, right? This seems trivial, but in our proof, the property of determinism will come very, very important to us. And you can sort of imagine that because we are using the determinism property in order to prove uh, the equivalence of programs, right, using simulation relation. If you have a non-deterministic program, like the one that you did in your operational semantics, right, if you just think about the big step semantics, even defining the simulation relation is going to be hard. Proving them is going to be much, much harder, right? We are not going to look at the non-deterministic programs um, in this course, but you can use similar techniques. It doesn't mean that you cannot use simulation. There is an extension of the simulation technique for non-deterministic programs as well. You do want to think about optimization for non-deterministic programs, right? Imagine I have a Go program. I want to apply some optimization that, say, removes creation of threads. And I still want to show that the program behaves the same way, right? So this is like a nice optimization because it has huge wins, right? So um, yeah, so that's an interesting problem that we are not going to deal with here. We are actually assuming that um, our semantics is deterministic, right? So we will sort of start with these two, and then we will dive into the actual proof. Okay. So okay, fine. So we close this. So okay. So let me make this a little bit bigger because this is going to involve a few terms. So the first thing is totality, right? So we said for all v comma c, right? This is very similar to unstuck. So either the command is already a skip command, or there always exists a v prime c prime that you can step to, right? So this is just a nice property that we have. The proof itself is not difficult. I am not going to go through the proof in detail. It's just a induction over the command structure, right? If you just do induction on the command structure, it will just naturally fall out. There's no complexity in this proof. I'm going to skip the proof, but if you want, you can step through it and find out what is happening. But that's a property that we have. Okay, and then there are a bunch of boring lemmas. Again, I'm not going to cover this. They are all in support for this determinism property, right? So the second property that I mentioned is our semantics is deterministic. How do we frame this? So for all VC, L, VC prime, if I can step 0 first from VC to L to VC prime, right? For all L prime, VC double prime, which I can also step to from VC, right? So this is one result of stepping. This is the other result of stepping. Determinism just means that L equals L prime and VC prime equals VC double prime, right? So if I am stepping from VC here, I'm also stepping from VC here. I'm just using different variables here, right? This determinism just says that these must be the same, right? So again, I'm not going to go through the proof in detail. This just falls out naturally. So once you do this for determinism for step 0 function, we have to lift that up to C step function. And what is in between step 0 and C step? It is the plugging in the context, the evaluation context, and so on. And that is why we have these lemmas that are sort of sitting over here. They are not that important. So I'm not going to cover them. Again, this is just a lifting up of the step 0 function, determinism property from step 0 function to C step function. Similar one, right? If VC can step to L VC prime, and the VC can also step to L prime VC double prime, then L equals L prime and VC prime equals VC double prime, right? So so this is also true. You'll just keep that in the back of the mind. We'll come back to it later, right? Okay, so we have we use these two properties which we sort of proved. What we are now going to do is we are going to generically prove, right, for any simulation relation R. What do I mean? What do we mean by simulation relation? It has this agreement property that they agree on termination, and it has this step property. We will call this one step, right? That if S1 can take a step with label L, then S2 can also take a step with label L, right? And the resultant states are related by this relation as well. So S1 prime and S2 prime are related, right? So the way we do it is we use the support for variables and hypothesis in Coq. We have not seen this before. I mean, all of these are sort of the same as hypotheses, right? So they are just different terms, but eventually they are all hypotheses. The idea is that we are going to make certain set of assumptions, right? And based on these assumptions, I'm going to prove a theorem, and the theorem that I'm going to prove is that trace equivalence holds, right? So I'm going to assume that there exists some relation R that I will later fill in for a particular optimization that I'm going to do. And what is this relation? This relation is a relation that relates two states, right? It has a valuation command on the left and valuation command on the right, and it's a proposition, right? So it relates some left-hand state to a right-hand state, and the relation has two properties, right? The first is agree on termination. So we have agree on termination here. And what does it say? If the left-hand side property, the left-hand side state is in fact skip, right? Then the right-hand side command is also skip, right? This is agree on termination that we have here, right? And the next one is this one-step function, which says that assume that VC1 and VC2, right, the pair of V and C, right, VC1 and VC2 are in fact related by the simulation relation. Then if VC1 can take a step by emitting the label L to VC1 prime, then there exists a VC2 prime, right, which VC2 can step to by emitting the same label L, right? The labels are the same, and the resultant states are also related, right? So what is written here is the same as the diagram that we have here, right? So we are just writing those down. And why do we use hypotheses? We are just saying that let's assume that you have this relation R, which is going to relate um, two states, and they have these properties, right? We are writing them down as hypotheses because we are just saying that let's assume that they have these properties. Now, based on these properties, I'm going to prove that the trace equivalence holds. I'm going to show first in one direction. I'm going to assume that I can take a step here. For every trace that is produced here, I produce an equivalent trace here. And I'm going to do backwards next, which is for every trace that is produced here, I'm going to produce a trace on the other side as well. Right? Let's do simulation forward. And what do I mean by the traces here? To formally translate it, let's say VC1, right, is the state on the left, and that state generates a trace NS, right? and for all VC1 and NS. So I'm not making any restriction on NS. And let's say that VC1 is in fact related to VC2. So this is sort of capturing this angle, right? So VC1 is related to VC2. Then VC2 also generates the same trace, right? This is what we want. So we are saying that, yeah, if the original program sort of essentially this translates down to if the original program takes a step and then produces some label, right, which is just the trace. The label may be silent. If it is silent, then I have to do the same silent label on the other side as well. If it in fact produces a label with a value, which is what generate captures, then I'm going to generate the same label on the other side as well. Right? And as I mentioned before, I'm going to prove this by induction on the definition of traces for VC1. Right? What are all the different ways in which I can generate traces? I'm going to induct on that, and I'm going to simplify in eauto to make simple rules go through. Actually, this proof is not too difficult, but you will see that there are two things that appear here, right? In addition to this R, I also have the hypotheses that I've just written down as part of the assumption. And the idea is that we can use these hypotheses as assumptions in order to make the goal go through. Right? That is what we are defining here. I'm going to induct on the first term, right, which is the definition of traces. Right? So I get one for each. The simple one is gone. The empty trace is gone because that's just gone with E auto. So, so firstly, what we are going to do is to say something about the final state, right? So what we have is left-hand side is already at skip, right? And right-hand side is VC2. Let's break it down to introduce the variables, right? We know it's a tuple. So when I do cases, it breaks down to V0C. I should, the proof obligation here says that V0C generates the trace none, right? And what do I know? I know that the left-hand side is V comma skip, right? But the property that agree on termination, what it says is that if the left-hand side is skip, then the right-hand side is also skip, right? That is what agree on termination gives us. So I'm going to apply agree on termination. This, right, unifies with this term. And what it will tell me is that C2 is in fact skip. Right, so I'm going to apply agree on termination on H. So I'm going to apply agree on termination on H and do the substitution. Essentially, I'm going to substitute skip for C. And what you will see is that you will see skip here. Right, you got this. And this is just constructor. At this point, this is just a fact. This is how we've defined yeah, so this is, if you do info auto, you'll see that it's just a direct application of gen skip. Right, that's the rule for the termination that goes through. Now we have two other subgoals that we need to prove. So this one corresponds to the left-hand side taking a step, right? C step VC to VC prime, emitting a silent label, right? And VC is related to VC2, right? And VC prime generates an NS. I need to show that VC2 also generates an NS, right? This is all a little bit all over the place. So I have a little figure drawn here, right? So, so this is the left-hand side. So VC takes a silent step to VC prime. VC takes a silent step to VC prime, right? And VC is related to VC2. That comes from H1, right? VC is related to VC2. And what do I have? I have that generate of VC prime is NS. So NS is a trace that is produced by VC prime. So NS is a trace that is produced by VC prime. I need to show that VC2 also produces the same trace NS. So VC2 also produces the same trace NS. And how do we show this, right? We have to, what do we know, right? So we know that by taking, by this one-step property, which the assumption that we made for the simulation relation, if VC can take a step, then VC2 can also take a step with the same label, right? This can also produce the same label none. And we know that these two are related as well. So VC prime and whatever is produced here will also be related by R. At that point, we can apply induction to make it go through, right? We have I head generate for us. We will use the induction to make it go through. Right? That's the idea here. So I will keep drawing these diagrams here, right? Just to explain how this thing goes through. So we are going to apply one step to actually get the fact that we can get a step here, right? And I'm going to do that as on H1. Observe that one step takes an R, right? The first thing is an R, then it has a C step, right? So I'm going to do the this one first. So this fills in the ones for C step. So that you get as a result. And what do you have? We have a conjunction here that comes from the conjunction here. So let's break it apart. Okay. And now what do we know? We know that VC2 can take a step, right? And by definition of one step, this is going to step by emitting a silent label, right? This is going to match one to one. So we are going to apply gen silent, right? This will say that show me that you can step from VC2 to VC prime. That is thanks to one step. We have a assumption here. So let me match that, right? And then this is the resultant state, right? This is going to be X on this side here. So generate X and S. That I'm going to solve thanks to induction hypothesis. At this point, you're sort of back to square one, right? You have a very similar shape to what you started with, and the induction hypothesis helps us get the rest of the way. So I'm going to generate in order to convert this to a goal which says VC prime is related to X, VC prime is related to X, thanks to, again, the induction, the one-step relation that says the resultant states are related as well. That is where this came from. So E assumption makes it go through. And you can relate from VC to, this particular property came down um, as a goal, sub-goal that we needed to prove. But that is in fact true, right? We know VC can step to VC prime with none. VC can step to VC prime with none. So that has been completed. So what we've done is that we have proved that if the left-hand side takes a silent step, right-hand side can also take a silent step and keep going, right? And the last case is if the left-hand side takes a step where it emits a label, the right-hand side also can do the same step and emit a label. This is exactly the same, right? There is no interesting bits here. Actually, it's the same as what we have here. So we are going to apply one step in H1 first order gen silent. Yeah, it's the precise same proof. So that goes through. What we have in fact done is we have sort of said for every trace that is generated by V1, if VC1 is related to VC2, then it also generates the same trace. We can now write it as a inclusion, trace inclusion, right? This is exactly the definition of trace inclusion that we have seen earlier. So I'm just going to say, if VC1 is related to VC2 by the simulation relation R, then all the traces that are generated by VC1 is included in VC2, right? So trace inclusion is defined exactly the same way. The proof is really simple. So you simplify it. This directly flows from the lemma that we just proved now. So when you apply that, you just get two sub-goals, which are essentially just assumptions, right? That goes through. Of course, you can just unfold trace inclusion and E-auto will make it go through. I can use it using this lemma. So this, I don't know whether we've seen this. You can use E-auto and then additionally provide certain lemmas that you're using. So E-auto using simulation forward. It also tries simulation forward at some point, right? So that makes it go through. So what we've done is we've done the forward proof. So every trace that is generated by the left-hand side is also generated by the right-hand side, right? And this is eventually we are going to use it as every trace that is generated unoptimized program is the one that is generated at least generated by the optimized program, right? The optimized program can have more traces, right? This inclusion is a subset, right? It only says that if a trace is produced by VC1, then it is produced by VC2. VC2 can have other traces, right? Um, according to just this definition. But really what we want is they produce the same trace, right? You don't want the optimized program to have additional behaviors. That would just be wrong, right? So you say your program prints 1 and you optimize it and it can print 1 or 2. That's not really what you want, right? You want them to produce the same set of traces. We've done inclusion in one direction. The second one we are going to do is inclusion in the other direction, which is that assume that VC1 is related to VC2. If VC2 generates NS, right, the optimized program sort of generates a trace NS, then that trace is also generated by the unoptimized program. So this makes sure that the traces are in fact the same. Again, we are going to do induction on the traces, right? But as I mentioned before, right, we are going to use the property that semantics is total and deterministic. So firstly, what we will do is we will just say, we'll just destruct a VC1 to bring out the fact that it is in fact a tuple, right? We are, so what we have at this point, if you sort of look at this, right, we know that all we know is that we have this R relation, right, that relates V0C to V skip, right? And I'm going to say something about V0C. And I need to show that V0C actually terminates, right? It's sort of emitting a trace which is only having the termination marker. But I have no property that actually says this thing can step, right? So I don't know anything by which I can prove that V0C can take a step. I only know something about the right hand side. I don't know anything about the left hand side. So this is where the totality property comes in handy. So what do you actually know, right? What do you actually know about V0C? We know that it is total. Either C is already skipped, right? Or that you can actually take a step from V0C to something else, right? So this is why we bring this fact into the context, right? So we do an assertion in order to bring this property into the hypothesis, right? You're saying the C variable is already a skip, or you can take a step from V0C to V prime C prime using the property that we already proved, right? By applying skip or step. So this is the totality property that we proved earlier. I'm just bringing that into the context. Okay, so all it's doing is that it's just bringing that into the context. It's already proved. So I have this property now. Now I can do case analysis on this, right? I can do first order. This breaks up, right? So if I do first order in substitution, there are two cases here, right? Either C is already a skip, or C can take a step. So that's what I get. So that's why I get one more sub goal. There are three sub goals here. Because I introduced something with the disjunction, I get two sub goals, right? So this is straightforward, right? When the program terminates, you just emit a termination marker. So that is easy. That goes through. Now, we have something interesting, right? So we say V0C is related to V comma skip, right? V0C is related to V comma skip. And V0C could be anything else, right? It could be anything at all. And V0C happens to take a step emitting X0, right? And going to XX1, right? Going to XX1. But observe that we have something strange here. We are saying that V0C is actually termination, right? We are actually going to show that this step can in fact not take, right? So this assumption that we are actually taking a step is not possible, right? So how are we going to prove it? We are going to prove it by applying one step. right? Now we are at a stage where the left-hand side takes a step. This one-step assumption shows that right-hand side should also take a step, right? But the right-hand side cannot take a step because it is already in a skip, right? So we are going to introduce that and prove it by contradiction. So we are going to first apply one step to one step says that you should be able to take a step if you take a step on the left-hand side, right? So we shall bring that into the context. Let's do first order to break it apart. Observe that you have this one now, right? Because of one step, what it says is that because you were able to take the left-hand side step, you should be able to take a right-hand side step. But right-hand side is already at skip, right? If you invert it enough times, you will derive a contradiction. So let's invert H once, right? Let's invert H4 now, right? So let's invert that. And now you see that there is a step zero rule from skip to something else. This rule does not exist. So it's a contradiction that goes through, right? So what we've done is we've sort of started here, right? We said we were here where we only had this particular step. And we said because we know our semantics is total, there should be an arrow, or C should already be a skip. And in fact, C can only be a skip. That is what we have in fact proved, right? So it cannot take a step. If it can take a step, then this can take a step. According to your assumption, that's not true. So that's what we proved using these two. I mean, using the totality and this one-step assumption that we have for the simulation relation, right? So yeah. So what I'm going to do is I'm going to stop here. And then I'm going to come back to this tomorrow, and we'll see the rest of the proof. So we will finish this, and then we will use it for optimization for our constant folding. Right. So let's stop here. Let's come back tomorrow. Thank you, everyone.